parles à droite, du coup.
Good afternoon and welcome to this conference. During the next 25 minutes, we will give you an overview about how 3DEXPERIENCE and CATFiber from Coriolis can help you design and manufacture composite parts, and more specifically, composite parts manufactured with automated processes. Oops, ça y est, ça commence. So maybe before going into the composite topic, just a brief view of what 3DEXPERIENCE is. So 3DEXPERIENCE is a platform which will allow all the people involved in the design of a composite product to collaborate around the virtual twin of this product. Using such a platform will allow to have a process which is much more efficient than having a more linear and a more sequential process. If we focus more on the composite aspect, usually what we see when we visit customers designing composite parts is that we have many people involved in the process of designing the composite part, and mostly we usually have design, simulation, and manufacturing people, each of them having their own process, their own tools. And of course, as any decision made by one of these people has an impact on the job of the other people, they have to exchange information, and this is done mostly through data exchange interfaces, which is slowing down the process and not helping to get the best quality at the end for the part. The value that a platform like the 3DEXPERIENCE platform is bringing is that all these people which are working on the same composite part will all work in the same environment, on the same data, and using tools which are all perfectly integrated. I will just illustrate that on two steps of the process, and starting by the very early stage of the process, which is the sizing of the composite part. So inside the 3DEXPERIENCE platform, you will find an application which will allow you to size, optimize the layup of your composite part. So here what you see is a function which will allow you to start from the design made, for example, by the aerodynamic engineer. So he's providing a surface, and you also have constraints like substructural elements that will be assembled to your part. With this tool, the stress engineer or the designer, both can use the application, will be able to isolate locations on the part on which it will be able to define specific thicknesses. That means amounts of material with given orientations. The application does not only allow to define the layers, the material, and the orientation on the part, but it has capabilities to simulate the behavior of the part. So it's an integrated application with design and simulation. As everything is integrated, we can go one step further and go to an optimization process. So what you have defined before is fully parameterized. So the designer can expose some of the parameters, like, for example, in our case in the video, the number of layers inside the different thicknesses assigned to the locations. And the designer can ask the system to make this number of layers vary. So here, for example, from 2 to 5 layers. Once these parameters are shared and defined, then the designer can decide to choose criteria that he would like to track and to follow. So you've got a whole list of simulation criteria that you can track. And for each of the one you have selected, you can decide what is your objective. I would like to minimize this objective. I would like to maximize this one, or reach a given target, for example. And then, once you have selected all your list of parameters with all the values, this gives you a whole set of different configurations that the platform will be able to simulate one after the other to find what is the best configuration fitting the requirement that you have defined at the beginning in terms of mechanical behavior of your part. So here we have the visualization of the different results while the computation is done. And when the computation is finished, the designer or the engineer will be able to select the one that seems to be the best for the objectives he has. And he can easily compare all this configuration in terms of number of layers, percentage of orientation, and of course on response to the stress that has been imposed to the part. So this was an example of the integration between the design and the simulation at the very, very, very early stage of the design. So we are just sizing the parts. If we move on in the process and go to the next step, which is the detailed design of the part, here the detailed design engineer, so the guy in charge of really providing the full detail of the part, will be able to start from the data created by the stress engineer at the first step. And as we need more information to design the complete part, he will be able to add information, so to enrich the model created. For example, in our case, we will define drop-off strategies that we will be able to assign at different locations of the part. So we keep the sizing model, we enrich it to go to the detail model, and once we have defined all the necessary information inside our detail model, the 3DEXPERIENCE will provide you tools to define the plies one by one, well, all the plies. So for example, first on the logical point of view, so just checking how the different layers will cover the different regions which were defined by the sizing step. And then having a preview of the final shape right before computing really the geometry. And then the next step being, of course, to create the final geometry of each plies. That's the information we will need at some point to go to the manufacturing step. So here I am computing the 3D geometry of each single layer using the logical definition combined to the drop-off strategy that I have defined before. With this, I have in the 3DEXPERIENCE platform a complete visualization or a complete modelization of my composite part. Still, at the end, at some point, I will need to include my composite part into a final assembly, and I don't necessarily need all the details. So I have the possibility to create a solid from my plies creation, and this solid can be included into an assembly so that I have the final product somewhere in my database. Very important, still the integration. Once I have done my final detailed design, I need to validate my design. So here we have in 3DEXPERIENCE platform simulation tools, which are integrated with the design tools. That means that the stress engineer will directly create the mesh on top of the geometry which has been used for the composite design, and can use composite design information to constrain his simulation model. For example, here, the stress engineer is constraining the mesh by the plies boundary which have been created before. Here there is a shell mesh which has been created first, but for some simulation we can make 3D mesh. So we have the capability to give a thickness to the mesh, and this can be done also using the solid that I have created before. So in fact, everyone is using the data that everyone has created. That's where the power is. And once I have created my mesh, I can easily connect the mesh with the layer information that I have created before at the design step. So just with one function, I can transfer all the plies definition onto the mesh so that my finite element model is ready to be used for structural simulation. So that was to show you the integration at the two previous steps, and François will show you how it works at the next step.
Thank you, Olivier. So if I summarize what Olivier was saying, working on the analysis and design worlds, you have the conceptual, the preliminary, and all this is optimized. So the platform allows basically to work concurrently on these topics, okay? And everything that is done with the platform that the 3DEXPERIENCE platform that Olivier has presented, the objective is to reduce the time it takes to go through all these steps and to maximize the time that people can do things not only in sequence but working concurrently. And this is what you've seen with Olivier. Now, if we move on to the, and sorry, I forgot to mention that here the objective is to optimize the mechanical properties of the part. Now, if you move on to the manufacturing world, let's say that the part that Olivier has presented, you want to program it with an AFP machine. You switch to other solutions for AFP programming, which generate programs that go onto the machine and then the rest of the process. Here are solutions like our CATFiber V1 solution, which is mainly on the Delmia side, so the manufacturing process simulation, or CATFiber, or any other solutions that are on the market and that are used today to program AFP machines. And the objective here is to optimize the production rate, to optimize the production of the part. And what we've noticed over the years is that these are pretty much separate worlds. It's true that a lot of effort is done by a lot of companies to have closer contacts between engineers and manufacturing designers, but it's still pretty much separate worlds. And the impacts of this is that the design is not always optimized considering the mechanical the manufacturing specificities. And the manufacturability of the part is considered late. Okay, the design is almost frozen, and the programmers are asked to program the part whatever it takes. To account for that, there are knockdown factors, engineering rules that are difficult to manage on the manufacturing side. It gives them a lot of constraints, which makes the programming pretty difficult. And what happens is that sometimes the automated fiber placement is not considered. So we stick to you stick to a hand layup, where you could have used AFP if you had had the tools to consider that as an option from the very start of the process. And the two main consequences of this is that you don't always reach the best compromise between the mechanical properties of the part, especially the weight, and the production rate. And it also leads to a high design to manufacturing lead time. Having different tools, different set of tools, makes it difficult. So what we've done with our CATFiber solution, which is a partner solution from Dassault Systems on the 3DEXPERIENCE platform, which is mainly on the Delmia side, more on the machine programming aspect, is to really separate it into two. One that is fully in CATIA, called DFM, CATFiber DFM, which allows to create or design the fibers how you want to place them on the part, where you want to place them, and an MPS solution, fully on the Delmia side, to actually program the part or program the machine to lay the fibers as they have been designed on the DFM side. And because the DFM is fully integrated in CATIA, CATIA being the designer's world, it can be used earlier in the process. You can use it, for example, at preliminary design, detailed design, and of course at the end of detailed design when you want to actually program the machine. At preliminary design, you can first define the theoretical orientations. It's quite surprising how much the theoretical orientations, 0, 45, minus 45, etc., orientations are considered without really thinking of the impact on the manufacturing aspect. So here you can start investigating how these theoretical orientations truly impact the manufacturing, and you might be able to change the theoretical orientations to make the manufacturing, the automated manufacturing, more easy. And also the surfaces. When it comes to aerodynamic surfaces, it's the aerodynamics that drive the surfaces. But for structural surfaces, you could make minor modifications to the surfaces and allow AFP down the road when it actually comes to programming the machine. The CATFiber solution, I'll show you a video just after, is a machine-independent solution. So true, Coriolis is known for being a machine vendor, but we developed this solution, this CATFiber solution, as a machine vendor independent solution, and you'll see that you can test all the machine heads that you want to test what it would give on your part. And because we've done most of the work earlier on in the process, it shifts the timing where of the actual machine programming, because it makes it easier to program the machine since you've taken that into account earlier in the process. So just to show you a quick video, it goes pretty quick, so I won't. I'll comment it just slightly before. You'll see that you can test different configurations. So when I say configurations, it's for example 8 times quarter-inch toes, 8 times or half-inch toes. I've given 3 examples in this video, and also see the influence of the theoretical orientations. So those of you who are familiar with rosette transfer, the impact of rosette transfer on the actual programming, on the actual fiber shapes. So the video here on the CATIA side, you see we're in the CATIA Composites environment, so really the designer's environment, and we're bringing AFP configurations between the number of being the number of toes, etc. And you can quickly create design. So here, this is 8 times quarter-inch with a standard rosette, and you see the type of design. You see that there is a steering impact on the rosette, on the design. And here, with an adapted rosette, it makes a slightly different fiber orientations, but it makes it possible to drape without having too much steering, which is one of the key points on the for AFP. And again, here we're in the design world. You can check if a head, whether it's a head on the market or something that you would like to have in the future, can actually fit in the part. So influence your surface. And here, this is the same example with 8 times half-inch, just to show with a bigger head. Okay, because 8 times half-inch, you'll have bigger heads on the market. You can actually check that there is a collision. There's no point making a perfect design if there's no head on the market that can drape that. And the conclusion here is that the part is AFP compatible. It just needs an adapted rosette, and here in this case, the best configuration is 8 times quarter-inch. And this, because you've got the true fiber orientation, the exact fiber orientation that you will be laying on the part, you can validate the part with simulation solutions, like with Simulia solutions, by sending these true fiber orientations to the fiber modeler, to the finite element model. And once this is done, the solution, of course, with the MPS side, the machine programming and simulation, allows to actually program the machine and simulate the movements of the machine and output a program that actually goes to the machine, to the real machine at the end. So I'm going to pass the hat on to Tobias, who will go further with the Delmia solutions on the path planning in the 3DEXPERIENCE. Thank you.
Thank you, François. So, as François has already told you, I am going now to talk a little more about Delmia. So how do we treat the information coming from CATIA, so from the design side, and how can we keep track on the side from resources and machine programming from Coriolis? This is being done in the Delmia PPR data model, and what PPR means is basically product, process, and resource. So that means we keep track between the product. You see we have 2 times the product. This is because we have, on the one hand, the product view from design stage, and on the other hand, the manufacturing view of the product, which is not always the same. Therefore, we need to make the distinction, but for manufacturing planning, we need to keep track on both of those views. Then we have the process plan, which means there I can define all the different steps and stations and my whole fabrication process of my production line. And to these operations then there are the work instructions linked for my workers when I have a manual production or workers on site. But as we are working on talking about automation, we use the resources, which are machines, and these are also linked to our process plan. And about the resources, François has already taught a little bit. I will talk a little bit as well, how we use our applications inside of Delmia for robotic and NC program simulations, and how we can extract the code of the machines and the robots to push all of this information then to production and to execution on our MOM and mesh systems. So let's see how this is being implemented for composites. So there we go. So as I already mentioned, we got the part from design, so from CATIA, which is the first line, the physical product of CATIA, and we create our physical or manufacturing point of view in our MBOM definition. In this case, as it is an automated process, it's quite simple. So we need the material, which is a material role inside of the machine, and then we need the quantity of how much quantity I need to produce my product. This is then linked to each other, and as we are working on the same environment in one platform, this stage can already begin once the first design phase has been done. So we are working quite in parallel together with the design department and the department of the NC programming from Coriolis. Then next step is I need to create and define my process planning, so all the different operations that are necessary to produce our product. I link all the different operations together, and as you can already see, our solution is 3D orientated. So you see a product build up going beside the different operations. So when I, at the end, have a look at my whole process plan, I can see how the product will be built up, coming from one operation to the next. So I need to assign my product. I need to then assign my resources, which I can see here now. So these are the 3D machines, so the Coriolis machines with the heads on the markets that François has described already, but also autoclave and also then robotic machines for quality control and final machining. And when we find out in the process planning step that we have missed something, or that there are operations that we might think that are necessary to include, or there are changes in the design phase, we can always come back and get the informations of change based on the change management strategy inside of the 3DEXPERIENCE. So once all the operations are defined and the product is assigned, we need to finally assign the resources, the correct resources that we have in our product layout to the operations. And then we see at the end the whole process. We can see the Gantt with the times and the product build-up concerning the different stations, the different operations over the whole process. And now we come back to the part where François has produced and manufactured the part on the Coriolis machine. And we will treat this then from with our robotic solutions to do quality controls, so non-destructive testing. Therefore, we use our robot surface simulation tool, which is an application that enables the users to create a simulation and create trajectories and tasks for robotics. For robots, all different kinds of robot manufacturers. And therefore, we use a database where we store all the robots. And then we can use those to keep in this, to create our trajectory for a robot, and then keep and see if, and validate the product in terms of quality. So let's have a look how this is working. We can see all the different axes of our robot beside. We can we have taught it either manually, either automatically. So there's a in the code, the software will analyze the surface of our product, and based on this surface analysis, he will propose a trajectory with teaching points, and then we can add, based on our robotic experts, if there are points that need to be added. And at the end, we can validate the robotic program and also the quality of our product, and export the robotic program to then execute it and push it to the robot on the shop floor. And at the end, we have another solution from our machining side to execute operations like final machining, which is our multi-axis machining simulation solution. And there we validate final machining operations, and here we keep track on the wear use of our tool, and therefore we can see it quite good on the picture. We can define a synodosal trajectory to minimize the abrasive and to minimize the tool wear of our tool, of the robot, and then utilize the resources as much as possible. And with this, we're at the end of the presentation. We covered nearly the whole process from design over resources and C programming to manufacturing planning. We will be now available for questions and remarks, and open to discussions with you next in the speakers zone for you. And if there are other questions, you feel free to come to our stands and booths, and we will be there the whole day and also the next 2 days as well.
Thank you.
Thank you for your attention.
Thank you.